All right, so we had the mean value theorem. We got the first video. So now we're going to do another video, and this is basically all examples. But the mean value theorem says that the instantaneous rate of change is equal to the average rate of change. But there are some conditions. We learned that it had to be continuous on the closed interval, and it had to be differentiable on the open interval. So again, we're going to put this in our memory banks, and we're going to use this. But I really enjoy not memorizing it and talking about it in terms of understanding. So the first example is use the graph of f, which I've shown, to estimate values of c that satisfy the mean value theorem for the interval to 0 to 8. And it could have been any interval. We'll do another interval after this. But we're going to do 0 to 8. So again, I'm going to use the purple line from 0 to 8 to estimate the average rate of change. And see how straight I can make it today. Oh, not too bad. That is the average rate of change. Now, I love smart boards because I can put a black line on there, and that is the same. But now I'm going to move that black line, hopefully. Yep. And I'm going to start looking for places where that black line, the instantaneous rate of change, is the same as the average. I see one right here. So the first thing, the first C1 I'll call approximately, I don't know, how about 0.9. And I'm going to move my curve then, and grab that line and pull it down, and I see another one right about there. So my C2 is about, I don't know, how about 2.8. That's a C here. I don't know why, a little dead spot on the board. I'm going to move down again and see, look for a third one going up, and I think there's another one right about there. In fact, almost exactly on 6. So I'm going to say the third point, C3, is approximately 6. And it makes sense. It looks there are 3 changes. And so I would estimate the 3 values on the interval 0 to 8 to be 0.9, 2.8, and approximately 6.0. If I change the interval, the answers change. If I change the interval, the answers will change. So if we change just a little bit of the problem, instead of saying 0 to 8, I could change the interval to 0 to 5. And I'm going to use a different color, 0 to 5. So 5 is approximately right there. I'll tell you what, let's not use 5 because that's not, I want to have a negative slope. Let's have 0 to 3. Again, continuous function, differentiable function. I should have started with that comment because those are the conditions that had to be met. So there it is. And if I now take my line here, I can see that I am looking here, and there are 2 of them approximately. There's going to be one again right about there, which I'm going to call 1.3. Maybe 1.2, but it doesn't really matter. And there's another one here, which I'm going to call 2.2. And you notice you work in the interval. You notice I don't pull this curve up here. I don't because it's locked inside the interval between 0 and 3. So again, continuous and differentiable, so therefore we make the function. Example 2 is, how about I give you a function, f of x equals 3x squared plus 5x plus 5. You should recognize that as a parabola opening up on the closed interval -1 to 1. Polynomial, so therefore it's continuous and differentiable. If we care what it looks like, we could make a quick graph on our calculator, which I did. And the interval is -1 to 1. So here's -1 on my calculator, here's 1. And it looks like -1 is awfully close to the vertex. So we're looking here for a line that's going to match. I think it's going to be about right here. All right, but I can't do this by calculator. So I know it's continuous and differentiable. Since it met those conditions, I'm going to say f prime of c equals f of b minus f of a over b minus a, where b is 1 and a is -1. So I get 2 on the bottom, 1 minus minus 1. And I'm going to calculate it up here. F of 1 is 3 plus is 13. F of -1 is 3. So I get 13 minus 3. Now, f prime of c. Well, let's start with f prime. Take the power rule. Bring 2 times 3 is 6. Take away 1 power 6. So it's 6x plus 5. Replace the x with C. If I get 6C equals 6C plus 5 equals 10 divided by 2 is 5. I get 6C equals 0. And don't get confused here. The slope isn't 0. This is just the answer. So if I divide both sides by 6, I get C equals 0. So the point where this happens is at 0. All right, where the instantaneous rate of change is equal to the average rate of change. So the instantaneous rate of change at 0 is equal to the average rate of change from -1 to 1. And again, this is pretty typical for calculus problems in college courses or AP courses. So a problem like this, right from an AP test. The value theorem guarantees the existence of a special point on the graph of y equals f of x between 0, 0, and 4, 2. What are the coordinates? Again, when you get to the AP at the end of the year, this will be an automatic problem. We know that 0, 0 is on the graph. We should have been able to, 4, 2. We know it looks like this. We know the average rate of change is this. We know that we're looking for the instantaneous rate of change to be the same. And if I use a different color. So somewhere in there probably, roughly. You don't need to have this, all right? But it just sometimes is nice. And again, you're defining f of x as square root of x then, right? Changing y. So the first thing I would do is write out f of prime of c is equal to f of b minus f of a over b minus a. And they gave us all the points. All right? If I make b equal to 4 and a equal to 0, f of a is 0, f of b is 2. So I get 2 minus 0 over 4 minus 0, or I get 1/2. And on the other side, the derivative of f of x is going to set this up as we're going to make a rational exponent, 1/2. So then do the power rule, f prime of x, bring the half down, 1/2 x, then take away 1, -1/2. So if I put c in at the same time, and I'm going to bring it down to the bottom, I get f prime of c is equal to 1 over 2 times the square root of c. So I'm just going to plug that in right here. And I love it when this works out this way, all right? I have students all the time say, well, what should I do at this point? I can see that c has to be 1. 1/2 to be 1/2. If you get confused, don't lose your algebra skills, cross multiply. All right? Square both sides, so c is 1. Is c between 0 and 4? The answer is yes, it is. All right? So that is the special point. The question then becomes, is 1, 1 the answer? Is the y value 1? So I go f of 1, and I go square root of 1. Well, obviously, f of 1 equals 1. I'm checking it against this function, where y is going to be f of x. So the answer to this problem is B. Then there's problems like this one we can use the mean value for. Last example for today. Suppose that f0 equals -3 and f prime of x is less than or equal to 5 for all values of x. How large can f of 2 possibly be? Well, we're defining an interval here. This might not look like the mean value theorem, but it really is. Now, you don't need the mean value theorem to solve this, though. So I'm going to try to do it both ways so you see it. F of x. So the first thing I like to do in cases like this is just kind of set a graph. Boom. And it's saying that the instantaneous rate of change is 5. So the most it can be is 5. Well, you know, the slope could be 5 going up. So we could just sit here and say, well, we know it can go up 5. And then we know it can go up 5 again. And we can say, oh, that's as steep as it could be, where the instantaneous rate of change is the maximum both times. And that's actually going to be the correct answer. We're going to use the mean value theorem to do it. Often in my test, I say use the mean value theorem to show how large could f of 2 possibly be. Well, we know the derivative of any interval is equal to the average rate of change. The instantaneous rate of change somewhere in the middle has to be equal to the average rate of change. And you might say, well, Mr. Anderson, what's the interval? Well, the interval is set here. the interval is going to be 0 to 2. And we're going to say the function's continuous, the function's differentiable. It has to be. So here we go. A continuous and differentiable function, 0 to 2. We know that b equals 2. We know a equals 0. We know f of a is negative 3. F of b is not known. Okay? It's unknown. That's what they're asking. How large can f of 2 be? And that said, we know that the derivative, if it's going to be how large, we want this derivative to be as high as possible. So we're going to set f prime of c equal to 5. And if you do that and fill in the equation, 5 equals f of b minus a minus 3 all over 2 minus 0. We get 5 equals f of b plus 3 over 2. Multiply both sides. You get 10 equals f of b plus 3. And we get that f of b, or f of 2 in this case, is 7. And again, if you look at the original graph, I didn't solve it the first time. Up and over 5, up and over 5. Well, what is that point? The point is 2, 7. And again, the mean value theorem works for that also. All right. Again, it takes practice, guys. This doesn't happen overnight. You have to do problems, and you have to keep working at it. The biggest thing is remember that the instantaneous rate of change is equal to the average rate of change on an interval where it is continuous and differentiable, and C will always be between A and B. Keep practicing.